Greetings. Lecture number 2, Ideal Gas. If you are new here, then you can go visit our lecture number 1. Here, there we have derived some important equation, gas equation, ideal gas equation, the pressure exerted by the ideal gas, and etc. But if you are here for revision, or you have already have some concept on ideal gas, then this is fine. You can go from there. Let's start. What we have in our previous lecture, that is, what is ideal gas, some basic kinetic theory or assumption of kinetic theory of gas, and how pressure exerted by an ideal gas, and some very important equation we have derived there. In this lesson we will start from the kinetic interpretation of temperature. We already have derived an equation that PV is equal to 1/3 of mn v bar square. Now we can write it in that way that 1/3 of mn v bar square can be written as 2 by 3 n and 1 by 2 m v bar square. This now this term is, we can say it, that is a term of kinetic energy, and as that velocity is the average velocity of all molecules, then that kinetic energy should be the average kinetic energy of all molecules. So that epsilon, we can denote that term PV is equal to 2 by 3 capital N epsilon, where average kinetic energy of the molecules are that epsilon. So this epsilon is the average kinetic energy of molecules. Now we also have PV is equal to mu RT. That's also we have derived in our previous lecture. Now that mu is N by Na, and that R is kilomolar gas constant. So we can write in that PV is equal to mu RT and PV is equal to 2 by 3 Ne. Now equate these two, that is N by capital Na RT. So from we can find that value of epsilon, that epsilon is equal to 3 by 2 R by Na T 3 by 2 kb T. Okay, now this R and Na both terms are constant, so that kb is the constant. That kb is called that Boltzmann gas constant. And another important interpretation from this is that kinetic energy is only dependent on temperature. Look, if we don't have mass and anything we don't need, uh, just we need that temperature to find the kinetic energy of any gas. So mass or any other have nothing to do with this energy, kinetic energy. Only temperature is important to find that kinetic energy. Now next we will derive the root mean square speed. We already have that kinetic energy half m v bar square, and that is equal to 3 by 2 kbt, and it can be written as also 3 by 2 r by nat. We are doing this both because we will find two different form of vrms, or root mean square speed. We can have easily that terms from this v bar square can be written as 3 kbt by small m, and that also can be written as 3 rt by mna. This term small m capital Na can be written as capital M, that is molecular weight of gas. So vrms is equal to, we already have the mean square of velocity speed mean square. Now root of mean square speed is equal to root of 3 rt by m capital M 3 kbt by small m. Okay, if we have this capital M temperature, we can find the vrms. Also if we have the small m and temperature, we can have the vrms. Now let's go to some important gas law. First one is Boyle's law. Okay, the PV is equal to 3 by 2 in epsilon. We know this term is a constant term. Mm, for the isotherm system, for an isotherm system, let's this is PV is equal to 3 by 2 by epsilon. The isotherm system means the temperature is constant. For a constant temperature, the pressure inversely proportional to the volume. Like, so P is equal to varies as 1 by V. Now look at this curve. Whenever the P increase, the V decrease, and whenever V increase, the P decrease. So that P varies as 1 by V. And now the temperature is varies into T. So if the temperature exists here, so that could be T by V. So the higher temperature, that the curve goes in this side. Okay, that if the temperature rise, this curve will be here. The next one is Gay-Lussac's law. That is, when the volume is constant, pressure is always directly proportional to their kinetic energy, and if it is directly proportional to kinetic energy, it's also proportional to their temperature. Now look at this um, system. It's called isochore. And look, if the pressure increase, the temperature also increase. Now for the, that can be written as P varies as T by V. So for the higher volume, the temperature will be low, and the for lower volume, that pressure, the temperature will be high, or pressure will be high. Okay, the next one is Charles law. That is isobar. For the constant pressure, that V will be directly proportional to temperature. Now look at this curve. As the T V get high, T also get high. Now that V, as PV varies as T and V varies as T by P, so the higher amount of pressure is the reason of lower amount of volume, and lower amount of pressure is result of higher amount of volume. Now let's deduct another important theory, that Avogadro's law. At constant temperature and pressure, equal volume of gas contains equal number of molecules. Consider two gas at the same pressure and temperature, then pressure can be written as 1/3 m1 n1 v1 bar square is equal to 1/3 m2 n2 v2 bar square. If you have not idea how we can get it, go through our first lecture. There we have derived this equation. Now look at m, that terms m and v terms. Both we have that m and v terms in that structure, that we can find an kinetic energy from there. Okay, and 1/3 will cancel out. The pressure is equal, and also we know the temperature is constant. So for constant temperature, the kinetic energy also temperature will be constant. So n1 is equal to n2. So that is the statement of Avogadro's law. What we have learned here, the kinetic interpretation of temperature. uh, from that we have derived that RMS speed. We have understand the Boyle's law and their curve, Gay-Lussac's law and their curve, Charles law and their curve, and the finally we learn Avogadro's law.